Hello? Hey, what's up? All right, hi clowns. Hopefully you can hear me. I don't know if you can or can't. Just let me know if you can hear me. Tashea, if you were not here, hold on. I was on the phone up until like a second ago. Okay, cool. Awesome. So there's a little bit of delay on the live stream. Shit, you can find what you're missing on Google Classroom. If you go into the Google Drive folder that I shared, it's all in there. You'll find like the actual worksheet, and you'll find an answer key. So you can go through it and then check yourself. Okay. For everyone else, hi. It's good to see everyone. I'm glad you all are alive in this very, very strange time. So, things that we could do right now, I could go through these notes really quickly. I could also answer any questions about 9.3 you may have. I got no questions from 9.3 via text, so I'm assuming that all of you are gods at it now and fully understand it. Or the most likely thing that happened was that y'all got a little lazy. Uh, Sorry, give me 1 second. Okay, so what would you rather do? Would you rather go over the key for 9.3 or talk a little bit about 9.4's notes? All right, I'm saying a 9.4. Sure, we can do 9.4. Okay, so this is about completing activities. I'm not going to go through this with you because this is your responsibility to finish, but I can talk through the notes. Okay, so with that in mind, here are the notes for this unit. So first we talk about a catalyst. What happened to my suit? I took it off because I had to go downstairs, and I didn't want to see my neighbors uh, look at me wearing a suit top and sweatpant bottoms. I feel like that would be weird, so I took it off. And now I'm wearing a hoodie, and this is my true spirit animal right here. How you change very quick? It's really just about a lot of practice. I'm really good at just putting buttoning clothes up quickly, I guess. Okay. Your favorite YouTuber. Great, thanks. So, I'm gonna go through 9.4, and then those of you that are feel good about 9.3, I'm not gonna touch it, and those of you that want to stick around and go over 9.3 with me, I'll go over it after. Okay. So, big takeaway from 9.4 is the idea of a catalyst. This idea that we have something that will increase the rate of a reaction or speed it up, make it faster, by providing an alternate pathway that lowers activation energy for a reaction. That's a lot of words. So, we're going to break this down step by step. The first thing you need to keep in mind is that when we have a reaction with when we have a reaction, we have the start point, we have an end point. And we know that for the reaction to actually start and work, it needs to go all the way from here all the way to the top. Yes, Trishana, this is for Chem. You'll see the physics video. It's already on the YouTube channel if you want to like look through it. I think it's about an hour long. Not the entire thing is like actual instruction. There's a lot of questions that are answered, etc. But you can kind of scroll through it and see which one, what questions work best for you, etc. Okay, so we have a start point. We have to get all the way to the top. Remember that the top is called an activated complex. Hold on. Okay. Uh, if someone has the Anabu's number, would you mind texting her the direct link to this chat to the stream because she's struggling to find it. Right. So we know the top of this is called the activated complex. So we have to go from the start point all the way to the top for the reaction to actually occur. Now, this requires some energy. In the case of this diagram, the activation energy, which is the same as the bond energy of the reactants, is going to be from 65 to 90. So it'll be about 25 kilojoules. So 90 to 65 is about 25 kilojoules. So I have to absorb 25 kilojoules for this reaction to actually work. Now, the advantage of a catalyst is that it lowers my activation energy. I don't need as much activation energy with a catalyst as I did without. Because when I add the catalyst, it's going to actually just let me go straight from 65 only to 75 kilojoules. How does that work? I know that last year you talked a lot about enzymes and what enzymes are. And the idea behind enzymes is that they'll help a reaction, speed up a reaction. What they'll do is they'll grab the two molecules that want to react and kind of orient them in the right way, proper orientation, so that they can react a little more easily. So catalysts are a more general word for enzymes. Enzymes are organic catalysts, but catalysts just anything that'll speed up a reaction. They'll do the same thing. They'll help rearrange these particles so that they can react a little more easily. And that reacting a little more easily means that we need less energy to actually start that reaction. So if we need less energy to start the reaction, it's going to give me an alternate pathway. When I think about pathways, I think about almost like, at least in this image, I think about climbing up a mountain. When you're climbing up a mountain, obviously, let's say that we had two paths to get from the start point of the mountain to the end point of the mountain. And the one way you could take is going all the way up here, and the other route you could take is just this little side route that goes along the side of the mountain. Which one is going to take more energy? Obviously, the one that requires you to climb all the way up is going to take way more energy. But we can find an alternate pathway, a different way to go around. And this alternate pathway will require less energy, less activation energy to actually work. The last thing I want you to realize is that it does not affect delta H. It doesn't affect my heat of reaction. Because my start point and my end point for both my catalyzed and my uncatalyzed reactions are the same. These are not changing at all. I am starting in the same place. I am ending in the same exact place. Okay, I know I just said a lot, so I'm going to freeze for right now. What questions do you have on this slide? Okay, I'm gonna move forward. I know that some of you are confused, and I feel like it's gonna be a lot more clear when we re-go over 9.3. But I'm gonna move forward for this right now. The rest of this is actually just straight up finishing the packet. So that's pretty much it. Yeah, heat of reaction is just delta H, Anaya. Gabriel, sorry. Anaya, what's the point of what? The catalyst? The whole point of the catalyst is to just make it easier for the reaction to occur. We have to do the homework for 9.4? Yes, Joby, that is going to be what's due tomorrow at 12. All of my physics kids, y'all could just hang tight and I will get to you. But right now I'm trying to focus in on what Chem is doing, so just give me a little bit of time to go through with the Chem stuff. Yes, I know, I have a very loud keyboard. Okay, so, thanks Natalie. Tell them not to go to physics. That's fine. Basically, Catalyst uses another route. Exactly, Tashea. Catalyst will go through another route. So instead of having to go this route that takes up all of this energy, this route with the uncatalyzed reaction literally has to start here and then go all the way up. A catalyst makes it easier. It doesn't require as much energy. So with a catalyzed reaction, I don't have to go all the way up. I can just go to right here. And if I go to right here, it's going to require way less energy, and I'm still going to get from my start point to my end point. Okay, I'm going to go back to 9.3 now, because I feel like that's something that we really need to go over. 9.4, y'all should be ready to go. Okay. Yes, you just have to send me photos of the completed packet for homework. That's correct. So now I go away. Okay. So I think we did a lot of this already. We talked about bond energy. We talked about the different activities that we were supposed to do. We talked about heat of reaction. And heat of reaction simply being... heat of reaction is just the difference between products and reactants. So if I give you a heat of reaction and I draw in a table... So let's say that I were to draw in one of my... This is not going to look pretty, by the way, and I apologize. Now, I'm going to draw it like this. This is going to be a exothermic reaction because I lost more energy than what I gained. This is my PER. This is my PEP. The delta H is simply the difference between my delta H, the difference between my products and my reactants. So I can calculate that using pepper. Pepper just means that delta H is equal to PEP minus PER. Abby, I promise you I'm going to figure out this homework thing. I see what you're saying. I need to focus on Chem right now. This is the equivalent of you walking into Chem class. Okay, what, Stephanie, the point of, like, listing these reactions, like, figuring out what this is. Okay. So remember that it would be useful for us to determine if something is positive or negative, like endo or exothermic, because then it'll help us figure out how much energy we need to use to get the reaction started. Now, the whole point of what's per product, potential energy of the reactants. Potential energy of the reactants. So, if we want to see how a reaction will occur, thanks, Anaya. Why do we use this? Like, in general, like the graphs and stuff, it's just meant to help us plot and figure out how reactions will occur. So, if I have a positively valued reaction, like an endothermic reaction, that means that I'm going to have to add a lot of energy to actually get the reaction to work. In an exothermic reaction, it's going to end up releasing energy. It will feel the heat coming off of it. And then the graphs are just meant to help us like diagram how this whole process works. Recognize that this whole process is literally indicating to us, okay, so we're starting at some place, we need to absorb this amount of energy, and then we're going to release this amount of energy. And it's just a way to graph that. That's all that we're really doing. 9.4 is homework. It's due by tomorrow at 12 p.m. Tomorrow at 12 p.m. means noon. It does not mean midnight. Tomorrow at 12 p.m. The catalyst is just another route. Yes, Jaylene, the catalyst is just another route. Can I give us the answers? No, that would kind of defeat the point of 9.4. I will give you the answers as soon as I check your homework, which will be tomorrow at 12. But Julissa, Julissa, you'll get a chance to check your answers then, okay? Okay, that's heat of reaction. We did parts of a potential energy diagram. We drew this out already together. Yeah, I don't think this is new. And then we just wanted to do some practice. Yeah, it's nothing crazy. It's the same stuff we've been doing. I could redraw this if you all want to see a drawing, like a full drawing with this information in it. We could do that together. I'm cool with that. I know, Julissa, I know you already did it, but the problem is that a lot of people haven't done it yet. Yeah, and again, remember that there's a little bit of stream delay, guys, so whatever you're saying, I'm seeing it like a minute. You're seeing what I am saying a minute after I say it. So you're going to have to wait a minute for me to answer your question. Okay, so yeah, I'm going to actually draw this out just to set y'all up with how to do the drawings. So draw potential energy diagram where the PE of the reactants is 300 kilojoules. Okay, let's do a drawing. So I got the whole thing. And again, this drawing is not going to be pretty, and I apologize. This is PE. This is time. Now, it says that I am starting where the P of the reaction is 300 kilojoules. So right here, 300 kilojoules. It says that the activated complex is 800 kilojoules, which means that I'm going to go up to like here maybe, and this right here is 800. And finally, the delta H is negative 100. If it's negative 100, this indicates to me that we have an exothermic reaction. It's an exothermic reaction. And exothermic, I know, has the shape where I have to end lower than I started. So this is my PER. My PEP. Good question to share. This is only potential energy. My PER, my PEP. My AC is up here. Now, when I were to label, if I were to label, what happened? Endo is spelled differently than exothermic. Yeah, it should be. I'm confused. Is a question from the packet? No, it's a question from the slides. I'm just going through an example with you to dream. So then we have my... I know that my delta H, which is the difference between where my PER is and where my PEP is. This difference right here. I know the difference is negative 100 kilojoules. So if the PER is 300 kilojoules and the difference is 100 kilojoules, it is, Ileana, it's similar to a 9.3 packet. It's the same general idea. And the difference is 100 kilojoules. This should be 200 kilojoules. Okay. So I figured out what my PEP was. I'm going to make a list right here of all of my values. I've got PER, which was given to me in the problem, and that is just 300 kilojoules. PEP, we just solved for. I'll explain how we solve for it again in a second. Tashea, that's a good question. PER, I'm gonna type it out in the chat. It's easier for me. Okay. Sorry for that rapid clicking session. This is 9.3. We're working through 9.3 right now. Yes, for that question, in 9.4, you will have to use the table. There's a question where you ask to use the table. Yes, and Julie, so the reason we don't have to use a table here is because I give you the information that you need even before the table. Okay. So we have PER is 300 kilojoules. We have PEP is well, we figured out that it's 200 kilojoules because we know that the difference is negative 100 kilojoules. We know that the activated complex, because we're given this information, is 800 kilojoules. We still have to figure out EAF. We still have to figure out EAR. And we know that delta H, because we're given this in the problem, is, I promise it's an H, is negative 100 kilojoules. Okay, so let's go through the rest of it. Now, I know that my energy activation forward is just this arrow here. Let's pretend that's a straight arrow. This is my EAF. And EAF is the energy of activation of the forward reaction. It's starting at my reactants and going all the way to the top. Now, we can do that mathematically, right? If we're starting at 300 kilojoules and we're going all the way to the top, all the way to 800, the value for EAF is going to be 500 kilojoules. And for EAR is just this arrow. Ooh, that's not good. We're going to start that again. EAR is just this arrow right here. And this arrow right here, we label EAR. And all that's saying is, if we started at the products and tried to go all the way to the reactants, what would the energy required to get to the top be? Well, we're starting at 200. We're going all the way up to 800. So that number would be 600. There's going to be a little bit of delay on what I'm writing and what you're seeing, but I'm going to post right now in the chat what questions do you have. Okay, so Ileana's asking where did I get 600 from? The 600 came from the fact that my PEP, my potential energy of my products, is at 200 kilojoules, and to get all the way to the top to 800 is going to be 600 kilojoules for my EAR. Jaylene, you have to explain what do you mean by it depends on where you start. I'm not sure what that means. And Julissa, you said huh, and I'm not sure why either. Okay, so let's go through it again. PER is just the potential energy of my reactants. I'm told that the potential energy of the reactants is 300 kilojoules. That's it. I'm told that my delta H, my heat of reaction, is negative 100 kilojoules. I drew that in here, negative 100. That's my delta H down here. Now, if my potential energy of my reactants is 300, and my delta H is negative 100, that means that my potential energy of my products is 200 kilojoules. That's because this is the difference. 200 is equal to 300 minus 100. Yes, Jaylene. So that would be just the EAF, the energy activation forward reaction. Thanks, Steph. Yeah, so Jaylene, so EAR is the energy activation reverse. If I start here and end here, and that's all the way up here, the energy activation forward is just starting here and going all the way to the top. So same idea, but you're starting here, going all the way to the top, and ending here. Julissa, AC, the activated complex, it just means the highest point on the graph. And that number was again given to us in the table. In the work problem, I should say. And what else? What else have I talked about? I think I talked about every single thing. Yes, exactly, Tashea. Catalyst is just an easier way, so you won't use a lot of energy. I want to use these same numbers. Adonis, this is freaking chemistry. Okay. I want to use this exact same like setup to explain catalysts. Okay, so let's do that. I'm going to erase the diagram. Sorry to those of you that were writing it down, but you can always go back in the video and check it again. Oh, this is the most inefficient way of erasing anything ever. Okay. So we're starting over. Now, I'm going to do the exact same drawing. So we're starting with my my PER at 300 kilojoules. My PEP ends at 200 kilojoules. PR and PEP. And we're going to say that blue is uncatalyzed. Blue is the uncatalyzed reaction. Now, I'm going to draw in the catalyzed reaction with red. Notice how I draw it, by the way. I'm starting at PER. I'm going to do these little like dashed lines. And I'm going to end at PEP. Now, again, my activated complex for the uncatalyzed reaction is at 800. But let's say that my activated complex for the catalyzed reaction is at 500. Okay. So notice what happened. My heat of reaction is still going to be the negative 100 kilojoules. Cool, thank you, Tashaya. Sounds good. My heat of reaction is still going to be negative 100 because I'm starting in the same place, oops, and ending in the same place. But what changes is my energy activation. Take a look. In my blue original diagram, my energy of activation for the forward reaction, we labeled as 500 kilojoules. And it's 500 kilojoules because I'm starting at 300 and going all the way up to 800. Question 2 in the classwork from today, Eileen? I'm assuming? Okay. Now, I'll give you a second to answer that, Eileen, because I know that there's a little bit of delay. Now, the difference is that now my EAF, and this is again, remember that red is catalyzed. My EAF for the catalyzed reaction, now I don't have to go from 300 all the way up to 800. Now I can just go from 300 to 500 because that's where my new AC is. So exactly, now it's 200 kilojoules. So notice what happened. Before it was catalyzed, I needed 500 kilojoules to start my reaction. So when I was talking all blue, when I was talking about the uncatalyzed reaction, I needed 500 kilojoules to get it to activate. Now that I'm dealing with the catalyzed reaction, it only takes 200 kilojoules. So, what did my catalyst successfully do? It lowered my activation energy. I now need less energy to start the reaction. And because I need less energy to start the reaction, it's just easier to start. That's the whole point of a catalyst. It's going to lower the activation energy. Now, the other piece of what a catalyst does is it does something that we say is called giving an alternate reaction pathway. Alternate reaction pathway means that I'm starting here, or I'm starting here. Well, I'm starting in the same place, actually. My bad. But I can either take this route or this route. So I'll give the example a little earlier. If this was like climbing a mountain, what would you prefer? To climb the mountain with this route or to climb the mountain with this route? Well, obviously, if you're lazy, you're going to want to climb the red path because the red path is a lot less energy. It requires less energy to go up. It's a lot easier to do it. So it's providing you an alternate pathway to get to your endpoint, to get to the area down here. So same idea in a reaction. We call it an alternate reaction pathway because it's just giving us a different way to get to the same place at the end. Okay. Guys, I think I'm going to end it now. I know that not everything is like still super clear, but I will be available until about 4:30, probably later. You could have done the graph over with red. I know, Stephanie, but it felt really busy. I am going to I'm gonna be on the phone pretty much all day, so you can text or call or whatever and ask me questions. And please take the opportunity to, because I think very few of you are gonna take that opportunity, and it's gonna kind of suck when it gets to like actually understanding all of this. Okay. All right. And I'm gonna wait like 2 more minutes for any last minute questions, and then I'm gonna hop off. So I'm gonna give you some time to give me some questions. Disgraceful. Awesome. Okay, clowns. I'm assuming there's no more questions. Email or text with them if you have them, and I will see you all later.